So in this video, I'm going to go over Stokes theorem. I did not get to fully discuss the theorem in class on the last day of class. So here goes. Let's again quickly review the Green's theorem, which is on about the line integral of a vector field over a closed curve. Okay, so here is a positively oriented curve enclosing a region in the xy plane. Then Green's theorem says that the line integral, which you can interpret as work of the vector field, is the same as the double integral over the region bounded by the curve of the curl of f dotted with k hat, and the integral is with respect to area. I want you to again look at the relation between k hat and the region. So looking at the region in 3D, the region is in the xy plane. Again, here is the same curve, positively oriented, and k hat happens to be normal to the region, okay, which is in this case the vector 0, 0, 1. Now, what if our curve is in space? Green's theorem is no longer going to be applied. So our curve is a space curve. It is closed. It's positively oriented. But assume that this curve is the boundary curve of some surface. This is that surface. Okay, so we're going to call that S. This is the curve. Okay, so this S is like the region, but it's not flat. Like imagine you have a hemisphere, okay? Hemisphere whose base is sitting in the xy plane. Then the curve is the circle of intersection of the hemisphere with the xy plane, okay? And let's also consider the normal to the surface. We all kind of know how to find the normal by now to the surface. And let's just say that the equation of the surface is z equal to g of x, y, as before. All right. Then if you're finding the line integral over this new curve, which is again closed, okay, again, Green's theorem can't be applied. The curve is in 3D. There is no region. But Stokes theorem says that, like Green's, this is a double integral, which happens to be a surface integral over the surface S of the curl of f, okay? But there is no k hat. We're going to dot this with n, and we're going to integrate it with respect to the surface. So this will be a ds. ds is the surface area increment. I mean, look at the resemblance of the two theorems, okay? Almost identical. Let's see how to find the surface integral of the curl of f. We've seen how to derive n. So let's just do some simplification, okay, on this surface integral, okay, so to evaluate the surface integral, you're going to have the double integral of the curl of f. Okay, now the curl of f itself is a vector field. It's a vector function. All right, but you're going to compose the surface with the curl of f. So this is going to be a function of x, y, and z is going to get replaced with g of x, y. All right, and then n, okay, we talked about n already. N is, remember, the gradient, n is the unit normal to the surface, which can be obtained by the gradient. The gradient made into a unit vector is the negative of g sub x, negative of g sub y, 1 over square root of g sub x squared plus g sub y squared plus 1, which is the magnitude, okay, of the gradient. And then ds, here is the surface area increment, which is g sub x squared plus g sub y squared plus 1 dA. Right, so this integral is dependent, the integrand is dependent on only x and y. And we're going to integrate over the projection of the surface in the xy plane. We're going to call that r of xy, okay? And we have orientation of the curve. If the curve is positively oriented, okay, so typically we associate that with counterclockwise, then we always take the upper n, okay, the upper n right there, not the lower n. Therefore, we take the positive of this unit normal, okay? If this was inward, which would associate with negatively oriented, then you take the negative of this, because in that case you get the vector with plus plus, and the k hat will be a negative 1, meaning that the vector is pointing downward. But we are just going to take it as is. And again, notice that these two cancel out. So the line integral of the vector field over the curve, which is again the boundary curve, happens to be the double integral over the projection of the surface that is in the xy plane of the curl of f, okay, at x, y, z again replaced with g of x, y, which again, this curl is a vector. You are going to dot it with the vector negative g sub x, negative g sub y, 1. I'm just going to copy paste that over here. All right. And again, so as we said, these get canceled. Integration is going to be with respect to area. All right. So again, here is the surface S. This is the boundary curve, right? Positively oriented. And this is the projection of the surface in the xy plane. Okay, now the surface can be given not as a function of xy. You could have x equal to g of yz. Then the projection will be in the yz plane, and y here gets replaced with g of x here will be replaced with g of yz. So there we go. This is another way to calculate a line integral. Remember that if the vector field is conservative, then the curl of f is automatically going to be 0. So as expected, you're going to end up with a 0 line integral. Okay? We talked about that before. Thus, to get this problem, problem 1, verify Stokes theorem. We have a vector field where S is the portion of the paraboloid. So it's a 4 minus x squared minus y squared. It's a paraboloid shifted up by 4. And it's opening downward because of the negative coefficients. That lies inside the cylinder x squared plus y squared equal to 2. Okay, I could have said instead that that the paraboloid is cut out by a plane, in this case z equal to 2, to create the surface here as you see. So just picture we have we have this paraboloid and we have a cylinder. Okay, the cylinder is of radius 2. Okay, the rest of the paraboloid has been cut out. All right, so just keep that in mind, and this is basically our S, and this is our C, the curve, the boundary curve is that. Okay, so we want to verify Stokes theorem. We want to do it both ways. We're going to do the line integral directly, and then we're going to use Stokes theorem to see if the answers match. Let's do Stokes theorem first. Let's do it using the surface integral. For the surface integral, I'm going to need the curl of the vector field. Hopefully the curl is 0. That makes everything simple. But the curl of the vector field so again, these are the partial derivative operators. And then we have y, negative 2, z, and 6 as the vector field. Let's find the curl. Okay, so we're going to have the partial derivative of 6 with respect to y. That is a 0 minus. We have the partial derivative of negative 2z with respect to z. That's a negative 2, so that will give us a plus 2. Okay, the second component, we take the partial derivative of 6 with respect to x, which is 0, minus the partial derivative of y with respect to z. That is also a 0. 0 is good news. And we have the partial derivative with respect to x of 2z, 0 minus the partial derivative of y with respect to y, that's a 1. So we know that our vector field is not conservative because the curl is not 0. The curl is 2, 0, negative 1. Okay, the curl of this vector field is constant. It doesn't depend on x, y, z. It's always the same at every point in the vector field. All right. Now, using Stokes theorem formula, we're going to have the double integral, okay, over the region in the xy plane of the curl. Let me just write it down. Well, I actually have a formula right there. So the curl of the vector field, which is 2, 0, negative 1. So now again, since the curl is constant, there is no z where I would have to plug in the equation of the surface into z. Okay, so we're going to dot that with the partial derivatives. Let's calculate the partial derivatives separately. Okay, so again, here is our g, that's g of xy, so g sub x is equal to negative 2x, g sub y is negative 2y. Therefore, again, based on the formula, we're going to dot it with the vector, the negative of negative 2x, right, which gives you 2x, the negative of negative 2y, which is 2y, and 1, okay? And this integral is going to be with respect to area, right? And it is done over the region, which happens to be, again, the projection of the surface, okay? You can confirm that this is a disk of radius 2. All you have to do is basically replace x squared plus y squared. Here with 2, you're gonna get z minus z equal to 4 minus 2, and that will give you z of 2. Okay, well, basically, again, you can see here that since the cylinder has a radius of root 2, not 2 but root 2, then this projection is going to have a radius of root 2. Okay, so let me draw that projection. All right, so that's the projection, r equal to root 2. Okay, so we can set up the integral over that projection. Theta goes from 0 to 2 pi. R goes from 0 to root 2. Do the dot product, you're going to get 2 times 2x, that's a 4x. And then 0 times 2y is 0. Negative 1 times 1 is negative 1. the a, okay, we're gonna write x in polar form, so 0 to 2 pi, 0 to root 2, that would be a 4r cosine theta minus 1, okay? And since we are doing the integration with respect to, integral in the polar system, we're going to have an r dr d theta. Now notice that here we have the integral from 0 to 2 pi of cosine of theta. We've had that discussion. The net area of the graph of cosine theta with the x-axis or the horizontal axis from 0 to 2 pi is 0. So this integral is just going to be 0, and we're going to basically get the integral from 0 to 2 pi, from 0 to root 2 of negative r dr d theta. Okay, so again, this is 0. So we end up with a minus, actually, a negative. All right. Again, if you notice, this integral is independent of theta, so I can do the last integral first, 2 pi, put the negative in front. The antiderivative of r is 1/2 r squared, going from 0 to root 2. All right, here we can cancel the 2 and a half and apply root 2. That's going to give us pi times 2. So 2 pi with a negative 2 pi. Okay, so the work done by the vector field to move a point or a particle around this curve is negative 2 pi. The vector field is doing negative work. Okay, so that's computation by Stokes theorem. Let's look at a direct calculation, which goes back to earlier sections. Okay, so, well, here we're dealing with a circle, right? So here we have an R. We have we need the parametrization of the circle. Okay. R, the radius is again root 2. So the best parametrization is root 2 cosine t, root 2 sine t. And the k-hat component, well, let's look at the picture here. The z here is 2. This circle is drawn at z of 2. Okay, so the k-hat component of the r vector is always going to be 2. Okay, while we're at it, we can calculate r prime. Okay, that is negative root 2 sine t, root 2 cosine t, and the derivative of 2 is 0. All right, so now we can calculate this line integral. Remember that for this parametrization, r is or t is going to always go from 0 to 2 pi to get the full circle. So this becomes the integral 0 to 2 pi. Let's look at our vector field. The vector field is y, negative 2z6. So plug in r prime's components into the vector field. Okay, so start with y. Right, so y here is root 2 sine t, so it's negative y, negative root 2 sine t. Let's look at the vector field again. I'm sorry, there is no negative here. I'm going to take that negative out. So it's just y. And then we have negative 2z. So negative 2, here z is 2. Okay, so again, applying 2 for z. And the last element of the vector field was just 6. We're going to dot this with dr. Remember, dr is just r prime dt. Okay? All right, let's do the dot product, which gives you a scalar, and you're finding the integral of the scalar. Okay, so here we have root 2 sine t times negative root 2 sine t. That should be a negative 2 sine squared t. Okay, then we have a negative 2 times 2, that's a 4. 4 root 2, negative 4 root 2 cosine t. And then we have 6 times 0, which is 0. So that's the integrand that we have to deal with here. Okay. Yes. So to run this integral, I have to do a power reduction on the first term, sine squared. Okay, so we have a negative 2. Sine squared happens to be 1 minus cosine 2t divided by 2. Okay? All right. And once again, here we have another integral of cosine t. I erased it. The integral of cosine t from 0 to 2 pi. That integral is just 0. You can check it. The antiderivative of cosine t is sine t at 0 to pi. That's just going to be 0. So this is what we're going to integrate only. Okay, so here we can actually cancel out the 2's, put the negative out. Okay, find the antiderivatives. So let me just show the cancellation of the 2's. The antiderivative of 1 with respect to t is just t. Okay, and then we have the antiderivative of cosine 2t, that would be 1/2 sine 2t, going from 0 to 2 pi. You can also argue that the integral from 0 to 2 pi of cosine 2t, again by the net area, by the net area theorem, is 0. Okay, you could see that if you put 2 pi or 0 into sine, you're going to get 0. All right, so this is just going to give you negative 2 pi. Okay, so as you see, the answers match. So negative 2 pi, we've gotten that using Stokes theorem. And negative 2 pi, we got that by direct calculation. Sometimes direct calculation is easier. In this case, it might be easier, but sometimes it's not. All right, so let's look at another example. This problem says use Stokes theorem to evaluate this surface integral. Okay, they're giving you a vector field and they're giving you s, or g of xy. Okay, now the way this problem is given is that it suggests that you should not actually do this surface integral directly. Okay, it says use Stokes theorem to evaluate that surface integral. And Stokes theorem says that the surface integral of the curl of f dot n ds is the same as the line integral over the boundary curve of f dot dr. So using Stokes theorem, instead of doing that, we're going to do this. All right. Yeah. And here S is again a hemisphere. And the boundary curve is basically, again, the circle of intersection between the hemisphere and the xy plane. So again, this is the hemisphere, okay? And this is the curve of intersection. Okay, so again, we're going to assume positively oriented curve. To find that curve, you just set the equation of the hemisphere equal to 0. And that gives you the circle of radius 2. Okay, so 4 is the square of the radius. All right, and again, the parametrization for that is r of t equal to 2 cosine t, 2 sine t. And since that curve lies in the xy plane, z is 0. And again, while we are at it, we can calculate r prime. Okay, and then we can now go ahead and evaluate this line integral going from 0 to 2 pi for the full circle. All right, now we are going to compose the curve into the vector field. Okay, so the vector field becomes 3 times y. Here y is 2 sine t. Okay, and then we have negative 2x, where x is 2 cosine t. So negative 2 times 2 cosine t. And then we have x, y, z. So you multiply all of these, which is just going to give you a 0, right? X, y are non-zero, but when you multiply with z, you get 0. So this is the vector field composed with R. And we're going to dot that with R prime. Let me just open up some room here. Because I don't have enough space to fit R prime. Okay, so R prime here is negative 2 sine t two cosine t 0 dt. That's dr. Okay, so when you do the dot product, this becomes a just a typical single integral. All right, so let's do the dot product. We have 6 sine t times negative 2 sine t. That's a negative 12 sine square t. All right, here we have negative 4 cosine t times 2 cosine t. That's a negative 8 cosine squared t. And then 0 times 0 is just 0. So that's what we get. Okay. Well, let's see what we could do. You can use the power reduction identity on both of these if you want. That wouldn't, that would not be a problem. Or you can attempt by expressing sine squared t in terms of cosine squared t. So you only have cosine squared t that appears in the integrand. But let me just go ahead and do the power reduction on each of these. I think it's a little easier. It's just less work. So we have negative 12. The power reduction for sine squared is 1 minus cosine 2t divided by 2. Okay, then we have minus 8. The power reduction for cosine squared is 1 plus cosine of 2t over 2. Okay, now again, the good news is that the integral from 0 to 2 pi of cosine 2t is going to be 0. Okay, so what we are integrating here is really 1/2 times negative 12. That would be negative 6. Okay, and then we have minus 1/2 times 8. So that's a 4 dt. Again, I have just dropped these terms because their integral from 0 to 2 pi is just 0. All right, so we're almost done. Here we have the integral from 0 to 2 pi of negative 10 dt, which is basically negative 20 pi. Okay, so that's it. You can attempt to do this problem directly, okay? Well, we have a hemisphere. Finding the partial derivatives, negative g sub x and g sub y, are going to create complicated expressions, right? And then imagine you have to find the curl of the vector field and dotted with the result for the part of the normal vector having to do with the surface. Do it directly and see what happens. I'm sure you're not going to have a good time. Okay, it's not going to be as really as easy. All right. But the line integral here is negative 20, which means that the vector field is doing negative work, meaning that we're going, if the particle is moving counterclockwise on that curve, it's going against the vector field. All right, let's look at this problem. Yes, so this says use Stokes theorem to evaluate. Again, we have one of those problems. The surface integral of the curl of f dot nds, they give you f. And they say S is the part of the cone between the two planes z equal to 1 and z equal to 3 with upper unit normal vector. Okay? Yes, so again, as suggested, we don't want to do this integral directly. You can attempt to do it directly. That's fine. Okay, that's not a problem, but it's going to be very difficult. All right, so here we have a cone between z equal to 1 and z equal to 3. All right, so let's say this is the circle of intersection when z is equal to 3. Okay. This is, let's say, the z-axis. Right? And here z is equal to 3. And then we have another plane, z equal to 1. Let's say this is the circle of intersection when z is equal to 1. Okay, so we have two curves. Let me call that C1, and let's call this C2. Okay, and this is the surface. It's just a part of the cone between the two planes. All right. Okay. So using Stokes theorem, this is what they want us to calculate. The surface integral of the curl of f. Okay. This is going to be the sum. Okay, we could break this up into according to Stokes' theorem, into two line integrals. It's going to be a line integral over C1 plus the line integral over C2. All right, so you have to do each of those line integrals individually and then add them up. Okay, so let's do the parametrization for C1. C1 is a circle of radius 1. Imagine you put 1 for z. Okay, that's going to give you x squared plus y squared equal to 1. So the parametrization for that is r. You call that r1 of t equal to radius is 1. So just cosine t, sine t, and that circle is when z is equal to 1. Okay, while we are at it, we can calculate r prime, which is negative sine t, cosine t, and 0. Okay, so our first line integral, okay, is going to be the integral, again, a full circle going from 0 to 2 pi. Okay, so take, this is your x, y, z, plug them into the x, y, z of the vector field. It is going to give you yes, it's going to give you y times z. So here y is sine t. Times 1, right? That's yz. Then the second component of the vector field is negative xz. So negative x here is cosine t times z of 1. And the k-hat component of the vector field is z cubed. That's just 1 cubed, or 1. Okay? And you're going to dot that with r1 prime. And integrate with respect to t. Okay, so let's rewrite this integral, 0 to 2 pi. All right, so multiply sine t with negative sine t. That's going to give you negative sine squared t. Okay, here we have negative cosine t times cosine t, negative cosine squared t. And 1 times 0 is 0, so that's it. All right, we can take out a negative from the integrand. And use the Pythagorean identity for trigonometry. You have sine squared t plus cosine squared t, which is 1. So you are really finding the negative of the integral from 0 to 2 pi of 1. Okay, that is just negative 2 pi. Okay, for the second integral, okay, so let's look at the second integral, which has to do with the with C2. For C2, z is 3. So if I put 3 to get the intersection of the cone and the plane z equals 3, I will get a circle of radius 3 because x squared plus y squared, you square 3, you get 9. The radius is really 3. So let's parameterize C2. I wrote C2 in green. C2, we can call that R2 of t. It is 3, the vector 3 cosine t, 3 sine t, and again, at that level, z is 3, so the k-hat component is 3. Okay, the derivative is negative 3 sine t, 3 cosine t, and 0. Now we are ready to calculate the line integral over C2. Okay, so again, compose R into the vector field, that's x, y, z. You get the integral from 0 to 2 pi. All right, so again, the vector field I hat component is y, z. Okay, so here y is 3 sine t. Times z of 3. Okay, the j hat component is negative xz. So we have negative x 3 cosine t times z of 3. And yes, and the k hat component is z cubed, so that gives you 3 cubed. I don't have the vector field on the screen. I'm just reading it off of another screen, but this was the vector field. We composed R into that vector field. And again, I don't have enough room to write down R prime, so let me resize this thing a little bit. Okay, so we're going to dot that with R prime. There. Okay, do the dot product. All right, so here we have 9 sine t times negative 3 sine t. That's a negative 27 sine squared t. All right, we have negative 9 cosine t times 3 cosine t. That's a negative 27 cosine squared t. And once again, 3 cubed times 0, 0. So we are left with this integrand. And once again, you can take out the negative 27 and get the integral from 0 to 2 pi of sine squared t plus cosine squared t, which is 1. Okay, and that gives you negative 27 times 2 pi. All right, and the answer here is 54 pi. All right, so finally, the answer, which is the surface integral, okay, of the curl of the vector field dotted with n is the sum of the two line integrals, which were negative 2 pi and 54 pi. And that gives you a total of 52 pi. All right, so this is the next problem in the handout. This time they're asking you to evaluate a line integral by evaluating the surface integral of the Stokes theorem. They're giving you a vector field, and C is the boundary of this plane in the first octant. Okay, let me see if I have it correctly. Okay, so again, Stokes theorem says that the line integral is the surface integral over the surface of the curl of f dotted with n ds. All right, and let's begin by finding the curl of f here. Again, hoping that the curl of f always is 0. And the vector field is x squared minus z squared. Might have to open up some room for that. Okay, j hat component is just y squared. K hat component is 2xz. Okay, so the curl is going to be the partial derivative of 2xz with respect to y. That's 0 minus derivative of y squared with respect to z, 0, negative of the derivative with respect to x of 2xz is 2z minus the derivative with respect to z of x squared minus z squared. Well, that's a negative 2z. So that will give us a plus 2z here. I was hoping that was a 0, but it's not. And then we have the derivative with respect to x of y squared, which is 0, minus the derivative with respect to y of x squared minus z squared, that's also 0. Resulting in the curl of 0 for z and 0. All right. Okay, so we have the curl. We have that, right? Now, next thing is to find g sub x and g sub y. So once again, here g of xy is the equation of the surface, which is 2 minus x minus y. So g sub x is equal to -1. G sub y is equal to also -1. All right, so let's set up this surface integral. Let's just call it I. It is going to be the double integral over the region in the xy plane of the curl. Okay, so the curl is 0 for z0. Now, for z, we're going to plug in the equation of the surface. Okay, so let me write the surface in pink. Okay, so 2 minus x minus y is going to get replaced into the z of the curl. Okay, so 4 times 2 minus x minus y. All right, the k-hat component of the curl was also 0. We're going to dot this with, again, negative g sub x. G sub x is -1, so the negative of that is 1. I'll just write it out, negative of -1. G sub y was also -1, so negative of -1. And by default, the k-hat component is automatically 1. So this is going to be integral with respect to area. Okay, so next thing we need is the projection of the plane, the projection of our surface onto the xy plane. To find that projection, we're in the first octant, by the way, that's good. Okay, so you want the trace, right? To get the boundary of the projection, you want the trace of this plane with the xy plane or z equal to 0. This trace is just the line x plus y equal to 2. Okay, so here is that projection. So again, we're looking at the part of the surface in the first octant. Its projection is going to be in the first quadrant of the xy plane. Okay, that's your r of xy, really. Now here obviously I can't use a polar I can't use the polar coordinate system. The region is not circular, so we're going to do a regular rectangular double integral. Here our x is going to go, or our y is going to go from 0 to the upper boundary, which is given by the equation of the line. Solve this for y. Y is 2 minus x. And within the region, x goes from 0 to an x of 2. Okay, so our integral is going to be x going from 0 to 2, y going from 0 to the line 2 minus x. And let us now do this dot product. Okay, so here we have 0 times that, which is 0. We have this component times 1, which is going to give you 8 minus 4x minus 4y. I could have just left the 4 out. And then within the dot product, 0 times 1 is 0. So this is what we are integrating. And the integrals with respect to y, then with respect to x. Okay, so this is one of those integrals that everyone is kind of reluctant to do. But I will let you do this integral. Okay, so just integrate with respect to y. Let me just get you started with it. So we have the last integral, which is with respect to x. Leave that alone. Integrate with respect to y. You're going to get 8y minus 4xy minus 2y squared. Okay, y is going to go from 0 to 2 minus x. Then we integrate with respect to x. Okay, so plug in, right? You have 8 times 2 minus x, right? So we're just applying 2 minus x onto y. The second term is going to be minus 4x times y, which is again 2 minus x, right? And then the last term is minus 2 times y of 2 minus x squared. Okay, and then you're going to integrate with respect to x. Now I suggest that you just square this thing at like terms and carry on with the integral. The final answer is going to be negative 16 over 3. So what did we just do? We calculated this line integral. Okay, line integral around the boundary of this plane, okay, which is going to be a rectangular, no, I'm sorry, not a rectangular, but a triangular boundary, right? Just picture that. You have the plane, right? In the first octant, right? It creates a tetrahedron, right? The boundary of the plane will be a triangular boundary. So, like that. Okay. So our curve is this triangular curve that we just found the line integral of. Okay. And instead of applying the line integral directly, which would create three different line integrals, right? You would have to do one line integral over this line, one line integral over this line, that's a C2, and one over this line. Instead, we used Stokes Theorem and did the surface integral of the curl of f dot n. Okay, so go through this example again one more time, please. And lastly, this says evaluate this line integral. All right, by evaluating the surface integral of Stokes theorem, they're giving you a vector field, and they are telling you that the curve is a circle. It's a shift to circle. Center is at 0, 3. Radius is 3 because you have 9 on the right hand side. And the orientation is counterclockwise. Okay. So again, we have the vector field, and we're not going to evaluate this directly because you would need to parameterize that, which is not a regular a cosine t, a sine t parametrization. This has a shifted, center. So the parametrization of that is not easy. And then composing r of t into f, which is already insane, is not going to be easy. Remember that you have to also dot that with r prime, okay? So evaluating the line integral directly is not suggested. Okay, so we want to use Stokes theorem. This is the curve is just a circle. Okay, and it is a circle in the xy plane. That's a circle in the xy plane. Right? So here's that circle. Right? It's in the xy plane. We're in the I'm not drawing the exact location of the curve, right? But this is your C going counterclockwise. It encloses a flat region, right? That's just a flat region. There's no surface, right? The curve is in the xy plane. So there is no surface. Therefore, instead of, taking some crazy surface, we can just take the xy plane as, right? Take this disk that's in the xy plane as really as the surface. Okay, so well, for that we need n. N is simply k hat 0, 0, 1, right? And I also need the curl of the vector field, Okay, so I am going to write down the vector field in the last row. All right, so let's calculate the curl. Here we have the derivative with respect to y of z minus x. That's a 0 minus the derivative of y minus z with respect to z. That's a negative 1, making that a plus 1. We have the negative of the partial derivative with respect to x of z minus x. That's a negative 1 minus the partial derivative of x minus y with respect to z, that's a 0. Lastly, we have the derivative with respect to y of x minus y, that's a negative 1. And the derivative with respect to x of y minus z, that's a 0. Well, we have here a constant curl for this vector field, which is basically 1, 1, and let me just make sure I did the last component correctly. Okay, so here we have for the last component, the derivative with respect to x of y minus z, which is 0, minus the derivative of x minus y with respect to y, which would be negative 1. So let me make a correction. So that should be 0 minus minus 1 or 0 plus 1, resulting in a curl of 1, 1, 1. Okay? So our line integral, almost done, over this curve by Stokes' theorem is the surface integral over the surface. And again, the surface is just this flat, flat region, okay, of the curl of f dotted with the normal, the unit normal ds, okay. We have simplified this to the double integral over the region, okay, of the curl of f, which is constant, therefore I don't need to find, I don't need to put the equation of the surface into the curl, right? Look, the surface is z equal to 0. G of x, y is simply 0, okay? So we're going to dot this with k hat, which is 0, 0, 1. Okay. Notice that if you want to do this directly, right, the derivative of this with respect to x is 0. The derivative of 0 with respect to y is 0, and you by default have 1. Okay. And this is going to be integral with respect to area. And this gives you the double integral of simply 1 dA, okay, over the region, right? And that is the area of the region, which is, again, the region is bounded by the circle of radius 3, okay? So it is going to be 3 squared pi, or 9 pi. All right, that should be the answer. Now, look, if I had taken some crazy surface as the surface whose boundary curve is this curve, like let's say I took a hemisphere, okay, or I took a paraboloid, the surprising result would be that I still end up with 9 pi. I do. So if you have some crazy surface, right, and the curve, you can just, you can just take a k hat instead of n of the surface. Okay, here we have surface independence, right? And this is these are applications of Stokes theorem. I hope this video was a little bit too long, but 5 problems with explanations. I hope it helps. Just make sure that you know that if they are asking you to evaluate a line integral and the curve is in 3D, right? You want to use Stokes theorem, okay? If direct calculation is crazy. And if they ask you to find this integral, right? Don't do it directly. They're saying use Stokes theorem to find this integral. So instead, we do the line integral, right? We saw that in the other example here. So again, this is just the same as the line integral. In this case, the line integral is easier than this integral where you would have to find the curl, right? And then negative gx, negative gy, 1, and then do the double integral over the region.